Karnataka produces some of India's highest value horticultural crops. Every year, massive volumes of temperature-sensitive commodities like mangoes, pomegranates, and grapes are pulled from the earth at an industrial scale. But before a third of that harvest ever reaches a consumer, it rots. For the producers, this spoilage translates directly to lost revenue. When farmers lack a way to preserve their crop during peak harvest windows, they are forced into distress sales, accepting rock-bottom prices just to offload degrading inventory. The standard response to this problem has always been to simply build more square footage of static cold storage. But laying down more concrete and legacy refrigeration does not solve the underlying math. Injecting traditional warehouses into a fragmented supply chain creates a more expensive environment for spoilage. Fixing this requires dismantling the current logistics model entirely. To understand why the old model fails, we have to isolate the specific structural breakdowns in the state's agricultural network. This graphic diagrams 6 exact failure points. High-yield zones face geographic imbalance, isolated from storage. Commodity mismatch prevents diverse crop handling. Poor logistics severs farms from transport. There's zero pre-cooling hardware. And active facilities rely on outdated, energy-intensive ammonia refrigeration, delivering limited scientific storage. The Karnataka Cold Chain Modernization Mission 2040 discards the static warehouse model completely. The new standard is an integrated, digitally connected logistics platform. This architecture demands unbroken thermal control, securing product temperature from the exact moment it leaves the farm gate until arriving at a global export hub. To eliminate the agricultural deficit, the state is engineering a unified stack where physical thermodynamics, constant digital monitoring, and structured financial models operate as one synchronized system. The bedrock of this new network is the multi-commodity facility. The rigid single-crop warehouse is being replaced by highly adaptable physical nodes. Different crops require entirely different thermal environments. These nodes are engineered with configurable chambers, capable of dialing exact temperatures from 0 degrees Celsius up to controlled ambient, allowing them to process diverse harvests year-round. Achieving that level of precise, continuous cooling requires a complete mechanical transition away from outdated systems to variable frequency drive, or VFD, screw and scroll compressors. Look at the energy profiles here. Legacy fixed-speed motors create jagged, high-draw power spikes because they only run at full capacity or shut off completely. VFD technology uses smart load balancing to continuously scale its power consumption, precisely matching the exact thermal demand of the chamber minute by minute. By eliminating those massive power spikes, the VFD mechanical upgrade drops total energy consumption by 20 to 35%. Coupling multi-commodity chamber design with VFD compression completely changes the economics. The node stops being a seasonal, high-risk cost center and becomes a year-round, highly efficient revenue generator. That mechanical efficiency is critical because energy is the single heaviest weight on the balance sheet, typically consuming 40 to 55% of a facility's total operating expenditure. To aggressively cut down grid dependency and peak demand charges, structural rooftop solar integration is now a mandatory design standard. This chart maps the facility's operating expenses. By generating 20 to 30% of the facility's required energy on-site, the total operating cost shrinks. This mathematically protects the project's internal rate of return from future utility tariff escalations. This is what these energy-optimized physical nodes look like in deployment, anchoring modern docking infrastructure directly below expansive, active solar arrays. In modern infrastructure finance, renewable integration serves a precise mathematical function. It is a strict requirement to secure institutional capital. Even with efficient power and cooling, relying on humans to manually monitor the environment leaves the inventory exposed. A single unnoticed hardware failure can wipe out millions of dollars in commodity value overnight. To fully automate environmental control, these facilities deploy programmable logic controllers linked to SCADA systems, instantly managing alarms and regulating every thermal zone simultaneously. But the architecture goes further, upgrading from standard preventive maintenance routines to artificial intelligence-driven predictive maintenance. IoT sensor networks installed directly on the hardware capture continuous, high-frequency streams of compressor vibration, current draw, and pressure data. The machine learning core analyzes those inputs against degradation signatures, generating precise maintenance alerts long before an actual breakdown happens. By identifying failures weeks before they happen, this digital layer significantly reduces the risk of unplanned downtime, providing a protective buffer for high-value perishable inventory. SCADA and AI convert passive, vulnerable warehouses into proactive, self-protecting assets. Of course, an intelligent AI-driven storage node is completely useless if the harvest arrives already thermally degraded from the field. Thermal control has to start the second the crop is pulled. Farm gate pre-cooling halts biological respiration by rapidly stripping field heat from the fresh produce. From there, continuous reefer transportation bridges the geographical gap, moving the preserved harvest from the rural collection point directly into the intelligent storage node. To make this technically viable for individual smallholder farmers, the system integrates farmer-producer organizations, or FPOs, aggregating scattered yields into commercially significant volumes. By aggregating through the cold chain, these FPOs grant farmers temporal price arbitrage. They can safely hold their inventory and sell it when market demand peaks, completely bypassing the harvest glut. World-class physical infrastructure only yields real economic returns when it is permanently synchronized with transport vehicles and farmer aggregation networks. Zooming out, every individual storage node, every IoT sensor, and every reefer truck links back to a single state-level digital command center. This Apex platform functions as a digital twin of Karnataka's entire agricultural logistics economy, providing real-time inventory tracking and macro-market intelligence. This organizational chart outlines the rigorous governance framework required to run it. Oversight flows from a Tier 1 Mission Steering Committee straight down to the Mission Directorate and the active private operators. Executing infrastructure at this scale is funded through long-term design, build, finance, operate, transfer, public-private partnerships. By structurally embedding climate resilience, low global warming refrigerants, and solar power into the design, the project aligns strictly with international ESG standards. As shown in the environmental and social pillars here, hitting these specific metrics unlocks highly concessional green debt. It is this precise combination of rigid institutional governance and ESG-aligned engineering that transforms agricultural policy into bankable infrastructure debt. This matrix summarizes target outcomes in the opportunities quadrant. The mission projects a 40% farmer income gain, leveraging SCADA and IoT. Precise visibility also captures sorting rejects for anaerobic digestion and composting, converting organic waste into biogas and fertilizer, integrating a circular economy. The thermal, digital, and financial efficiency of this logistics architecture now dictates agricultural dominance, outweighing the raw productive capacity of the soil itself.